Okay, so today we're looking at proof by induction, and we're going to be looking at those induction or those proofs required to that involve sums. So our learning intention is the knowledge of the process of performing proofs by induction. We'll be successful if we can prove that the base case is true, assume true for n equals k, prove that's true for n equals k plus 1. In addition, we want to describe what a proof by induction is and recognize and comprehend sigma notation. So looking at these two things first. Proof by induction is a formal mathematical proof. There are 4 steps. The first steps, they include proving the base case, assume it's true for n equals k, prove that it's true for n equals k plus 1, and then conclude. So those are the steps we do every time we do a proof. The idea is that you have some examples of using dominoes. If you have dominoes lined up, if we can prove that the first domino falls, we want to then prove that all the other dominoes following it falls. And we can do that by proving the base case, the first domino falls. Then prove that it might fall for somewhere down the track. And if that one falls, then it means that the other one, the one that follows that one, would also fall. And if that happens, then all of them should fall together. Okay. A lot of the things that we'll be dealing with, if you haven't done series and sequences yet, it doesn't really matter. But just a quick cap is just to understand, if you have a pattern of numbers, we call that a sequence. Such as this is the Fibonacci sequence, or sequence of all even numbers. As soon as you put a plus, an addition or subtraction of these things, it becomes a sum. Okay, and so what this means is that we're adding all the odd numbers, all the even numbers, and basically this formula is have the position and then add 2. Yeah, so or add 1. Yeah, or odd numbers should be 2. Yeah. Oh, sorry, 2n. Yeah, so if the first position was 1, so 2 times 1 is 2. Second position is 2, so 2 times 2 is 4. Third position is 3, so that's how we get these numbers, and that's what it means by this. If we were to add all the numbers going up to a certain number, that becomes a series, and we denote the sum of that with this capital Greek letter of sigma. Yeah, which you may have seen that in Excel or some other spreadsheet program. It just means the sum of all those terms together. Okay, so let's do some proofs through examples. So we want to prove that 1 plus 2 plus 3 plus 4 all the way plus n is worth n multiplied by n plus 1 over 2 for all integers when n is greater than 1. So I'm going to do the 4 steps. The first step is always, step 1 is to prove the base case. And in this situation, the base case is when n equals to 1. Yep, because we're going to say n is greater than or equal to 1. We could have a base case where n equals 0. Yeah, and all we have to do is then would let n equals to 0. We don't usually have anything past that because it would be counterintuitive. You can, but in this course we definitely wouldn't. Okay, so here we would have let n equals to 1. So the left hand side, yeah, n equals 1. The right hand side is n plus 1 over 2. Well, that's 1 lots of 1 plus 1 over 2, which is 2 times 1 is 2 over 2, which equals 1. So the left hand side is equal to the right hand side. So statement is true for n equals 1. And what that means is that the first domino has fallen. Step 2 is we want to assume statement is true n equals k. And so we're going to write down, assume statement is true for n equals k. So it means that 1 plus 2 plus 3 plus 4 plus all the terms up to k is equal to k times k plus 1 over 2. Okay, and that's just basically substituting k every time you see n. Okay. Step 3. So step 2 and 3 is what we call the inductive step. And we want to prove that this is true for n equals k plus 1. So if a domino falls, the next domino behind it will fall. Okay, so we're required to prove that n equals k plus 1 is true. So we get 1 plus 2 plus 3 plus 4 plus k, all the dominoes before it, plus k plus 1 is equal to, now we're replacing k plus 1 in all this stuff that we see. We get k plus 1, that's for that part. Now if I put k plus 1 and I add another one, that's actually k plus 2 all over 2. Okay. So let's play with the left-hand side. We want to prove we've got 1 plus 2 plus 3 plus 4 plus k plus 1. Now, this section here, we know what that is. Yeah, we know that that is worth this. Yeah, because this is the same here, and we're saying that it's that. So using our assumption, we can replace this with k plus 1 over 2, and we want to add it to k plus 1. Alright, well that's just the same as k plus 1 over 1. So we've got two fractions. We're going to basically multiply this by 2, so we get k plus 1 plus 2 lots of k plus 1. That's all over 2. Okay. Now, using the technique of grouping in pairs, we've got k plus 1 and k plus 1. Well, that is just k plus 1 times k plus 2. So grouping in pairs. That's all over 2. Well, that is equal to the right-hand side. Yeah, that's the same as that there. Okay. So step 4 is the conclusion. Okay. Okay. So I should actually write, so statement is true for n equals k plus 1. Okay, so the conclusion here I'd write the statement is true for n equals 1, so it must be true for n equals 2, 3, 4, and so on. So the statement is true for all integers when n is greater than or equal to 1. Okay, that's your first example. Okay. Example 2. We want to prove that a half plus 1 over 2 squared plus 1 over 2 cubed plus all the way up to 1 over 2n is equal to 2n to the power of n minus 1 all over 2n. So step 1, we want to prove the base case. So we're going to let n equals to 1. Yeah, so the left-hand side is 1 over 2 to the power of 1, which is a half. And the right-hand side, so that's the left-hand side was just substituting n equals 1 for that. The right-hand side is this part, so we get 2 to the power 1 minus 1 over 2 to the power 1. We also get a half, because 2 take away 1 is 1, and 2 to the power 1 is 2. So the left-hand side equals the right-hand side, so statement is true for n equals 1. Step 2 is the assumption for n equals k. Yeah, so we're going to state, assume true, or statement is true for n equals k. We're going to show what that means. So that means a half plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2k, yeah, is equal to 2k minus 1 over 2k to the power of k. Sorry. Okay. So step 3 is where we have to require to prove n equals k plus 1. Okay. So we are required to prove that n equals k plus 1 is true, or holds true. So that means we get a half plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the power of k plus 1 over 2 to the power of k plus 1. So the next term, so these are all terms up to 2k. The next term is 2k plus 1 is equal to 2 to the power of k plus 1 minus 1 all over 2 to the power of k plus 1. Okay. So the left-hand side, we're going to prove the left-hand side first. We get a half all I'm doing is rewriting the left-hand side. Okay. I know what this section here is. Yeah. Because that is basically this part here. So I'm going to state using my assumption. We get 2 to the power of k minus 1 over 2k plus 1 over 2k plus 1 to the power of k plus 1. Okay. Now, this part here, so I'm just going to write it up here again. So we do 2k, and instead of writing it as 2k plus 1, I'm going to write it like this. I'm going to write it as 2 multiplied by 2k. because the bases are the same. That's 2 to the power of 1. When the bases are the same and we're multiplying, we add the powers. This really is 2k plus 1. Okay. So to make them the same, so they're adding fractions now, we've got 2k minus 1 over 2k. I really want this to be multiplied by 2. And we're going to add 1. Okay. So if I just expand out, I've got, that's really 2k plus 1, multiplying those two together. 2 times negative 1 is negative 2 plus 1 is negative 1. So this is 2k plus 1, because I times this by 2. Yeah, which is 2k plus 1. Okay, now that is what I wanted to prove as the right-hand side. Yeah, so I should write, so statement is true for n equals k plus 1. So step 4 is the conclusion. The statement is true for n equals 1. So it must be true for n equals 2, 3, 4, and so on. So the statement is true for all integers when n is greater than or equal to 1. Okay, third and last proof. Alright, we want to prove that 1 squared plus 2 squared plus 3 squared plus all the way up to n squared is equal to this. So step 1, the base case. Okay, so we're going to let n equals to 1. We get the left-hand side, we get n squared. That's 1 squared, that equals to 1. The right-hand side, we get 1 over 6 n plus 1 to n plus 1. That's 1/6 times 1 is just 1/6. 1 plus 1 is 2. 2 times 1 is 2 plus 1 is 3. 2 times 3 is 6. And 1/6 of 6 is 1. Okay, so left-hand side does equal the right-hand side. So statement is true for n equals to 1. Okay, step 2. We want to prove. We want to assume the assumption. Okay, so assume statement is true for n is equal to k. And what does that mean? That means that 1 squared plus 2 squared plus 3 squared plus k squared is equal to 1/6 of k, k plus 1 over 2k plus 1. Okay. Step 3. So remember that step 2 and step 3 are called the inductive step. We're required to prove n equals k plus 1. Okay. So we are required to prove n equals k plus 1 is true. So we're trying to prove that the 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1 squared, all squared, is equal to 1/6. We want k plus 1. K plus 1 plus 1 is k plus 2. And then 2 lots of k plus 1, that's 2k. 2 plus 1 is 3. Okay, that's what I need to prove. So the left-hand side, we've got 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1 all squared. Remember that we know what this is using our assumption. We know that it's that. So we've got to state using an assumption of n equals k. We've got 1/6 of k, k plus 1, 2k plus 1, that's subbing that for that, plus k plus 1 all squared. Okay. I could take out a factor of k plus 1 and then put everything else later, or I could do this. Okay. I could do, if I, I'll expand this part first. So I get k squared plus k, and I'll expand that, so k squared plus 2k plus 1. Alright, expand this out a little bit more. I get 1/6 2k cubed plus k squared plus 2k, so plus 3k squared plus k. And what I'll do is, if I want to add these two together, this has a factor of 1/6, so I've actually really multiplied this all by 6. Alright, so I keep my 2k cubed. 3k plus 6k is 9k squared. 1k, and I want to multiply that at 6, so that's 12, plus 1 is 13k, and plus 6. Okay. Now that doesn't look like that at this stage. And because the new course has taken out cubic factorization, what I'm just going to do is I'm just going to get the right-hand side and I'm going to expand the right-hand side. So the right-hand side is equal to 1/6 k plus 1, k plus 2, 2k plus 3. I'm just going to expand that. So it's k squared plus 3k plus 2. Keep expanding that out. So we get 2k cubed plus 6k squared plus 4k plus 3k squared plus 9k plus 6. Collecting like terms. 6 plus 3 is 9k squared. 4 plus 9 is 13k plus 6. Now that does look like this. Yeah. So we can now state that the left-hand side is equal to the right-hand side. Yeah. So our last step is to conclude. So I should have so statement is true for n equals k plus 1. Okay, so the conclusion is the statement is true for n equals 1, so it must be true for n equals 2. 2, 3, 4, and so on. So the statement is true for all integers when n is greater than or equal to 1. Okay, and that is all the proofs. So remember, this is about proving of induction, has 4 steps. You need to prove the base case. You need to take the assumption it's true for n equals k, and then you need to prove that it's true for n equals k plus 1 using the assumption, and then conclude. Okay, thank you very much.